Hello chemistry students. In this presentation I'm going to go over gases or at least give you an introduction to gases. So gases show up in a lot of places, from hot air balloons to the atmosphere of the planet to helium balloons to even the gas that inflates the airbag to keep you from banging your head on the steering wheel in a crash. Alright, so just to review a little bit, 3 states of matter are solid, liquid, and gas. And so the gases are the part when the particles of whatever substance are the farthest apart. They're not held together well by intermolecular forces at all. Windy day is a result of a difference in pressure between gases. So whenever there's a pressure differential, the gas will move from high pressure to low pressure. There are some characteristics of gases. They're highly compressible, meaning you can squeeze them together, like what happens when you pump up a tire or a basketball or a football or something. You're putting those gas molecules and pressing them close together inside of the container. Gases are thermally expandable, meaning that when you heat them, they move farther apart. They flow easily. They have low viscosity. Most gases have very low densities, like about 1,000 times less than the density of solids, most solids and liquids. Alright, and there are no solubility rules for gases because they're infinitely miscible, meaning that you can mix them in any proportions, or you can have any type of contaminant in the air that you breathe too. Alright, so kinetic molecular theory is the theory that describes the behavior of ideal gases. So the particles within a gas travel in a straight line motion and obey Newton's laws that includes when they collide with each other and change directions, which I'll show you in a moment. Let's see, particles in a gas occupy no volume. Real gases actually do occupy a little bit of volume, so sometimes the volume prediction by the ideal gas law is a little bit lower than the volume of real gases. Let's see, collisions between particles are perfectly elastic, meaning they don't lose or gain energy overall during collisions. There are no attractive or repulsive forces between the particles. We know that, again, this is for ideal gases. Real gases do have some attractive forces, otherwise they wouldn't become liquids or solids. So you can go back and look at intermolecular forces for that. Some gases will deviate more from the ideal gas law than others. And the average kinetic energy of the particles depends on the temperature. So the hotter the gas sample is, the higher the average kinetic energy of the particles within it. Alright, so let's jump over and look at this PhET simulation a little bit. Alright, so let's put some gas particles in here, and I'll give them a moment to kind of move around here. And you can see that they do move in straight lines until they bounce in and hit another particle. But you can also see that over time the temperature is not changing. And if we left this along long enough, the pressure would eventually equilibrate as well. So you can kind of see that's a visualization of what gas particles look like in the actual room. Some of these would be moving 300 meters per second, which is pretty fast. It's right at the speed of sound. And you can also see that some particles travel a very long way before they interact with other particles. Alright, now back to the presentation. Alright, so let's talk about, I'll go through these quickly. Alright, so on Earth, when you drop a ball, it converts kinetic energy potential energy into kinetic energy. But it doesn't keep bouncing forever, because energy is lost to frictional forces. However, with gases, no energy is lost. So this is kind of like what an elastic collision would be if it just kept occurring. The ball would bounce as high every time, which would be kind of fun and kind of crazy at the same time. But in the macroscopic world where we live, if there are inelastic collisions that lose some of the kinetic energy every time. So gases behave like this. They don't lose energy. Macroscopic objects do. All right. So the properties of gases are modeled with a few different quantities. So the first of these is the volume, and that is how much space or the size of the area, the volume that the gas takes up. Usually we'll measure that in liters. Occasionally it'll be presented in milliliters, and if you're using the ideal gas law, you will need to convert to liters if you're not already in liters. Temperature for gas properties and gas laws will be measured in Kelvin. And if you're in Celsius, then you need to convert to Kelvin. There is an equation that tells you how to do that on page 3 of your reference table. It's the second equation. Basically, if you have a Celsius temperature, you add 273 to it to get the Kelvin temperature. If you don't use the Kelvin temperature, then the gas laws are no longer proportional, and that's no fun because you'll get the wrong answer every time. All right, the amount of the gas, the number of moles, is represented with N, and the pressure, usually we'll do that in atmospheres, but you could also measure pressure in other units. All right. Standard temperature and pressure are defined as follows. So standard temperature is 0 degrees Celsius or 273.15 Kelvin. If you ever forget this, it is listed on page 1 of your reference table, so you can look that up. This was convenient for chemists to use because the way you get 0 degrees Celsius in a lab is you put ice in water and make an ice bath, and it'll be at 0 degrees Celsius or 273.15 Kelvin. Standard pressure is, by the way, you can just use 273 for most calculations and it'll be fine. Standard pressure is defined as being 1 atmosphere or 101.3 kPa or 760 millimeters of mercury or 760 torr. And I'll actually show you how to do conversions amongst those in just a moment. Okay, air pressure results as a downward force or as a result of the downward force of all the air molecules above your head, also described as the column of air above you. Kind of like when you swim down to the bottom of a pool, you can feel the pressure increases. Same thing with the atmosphere. As you go higher, the pressure decreases. Pressure is force per unit area, or in other words, the weight of the air column divided by the area that it covers. Okay. To measure this, a scientist whose last name was Torricelli actually had a tower that he was doing experiments like this, and he started out with water and then replaced it with mercury, and he noticed that on an average day the height of the column that would form inside of this tube was 760 millimeters, and when the weather was going bad, it would go down, and when the weather was going up or getting better, then the column of mercury would rise, and that gives us the idea of barometric pressure, because the atmospheric pressure pushed down here, so when it's high pressure it makes this rise, and when it's low pressure it sinks. All right, so different ways that you can measure pressure here, several units. You can do inches of mercury, which is what the National Weather Service reports in. You can do pounds per square inch. You can do kilopascals, or even feet of water. Okay, so let's do a couple of conversions here. If we wanted to convert 500 40 millimeters of mercury to atmospheres. Remember, all of these things are equal, so we can do conversion factors. Again, those are on page 1 of your reference table if you ever forget. So our unknown is the atmospheres, our known is the millimeters of mercury, and our plan is going to be to use the fact that 1 atmosphere equals 760 millimeters of mercury as a conversion factor to set this up. So always start with your known, do the train tracks, and set it up so that the units will cancel out. So you put the millimeters of mercury on the bottom and the atmospheres on the top. Multiply across the top, divide the top by the bottom, and you should get 0.711 atmospheres. All right, the pressure in kPAs. So our process will be very similar, except, so we'll start with the same thing, but this time we'll do 760 millimeters of mercury equals 101.3 kPAs, and cancel out the units and multiply the top, divide by the bottom, and you should get 72 kPAs. All right, torrs to millimeters of mercury. If you look back, you would see that there's torrs and millimeters of mercury. Both are 760, so 920 torrs is 920 millimeters of mercury. All right, so let's go through some gas laws really quick here. We're in the next presentation, we'll put these together in a combined gas law, but let's talk about Boyle's law. So as gases get more compressed, the pressure goes up. This is described with P1 V1 equals P2 V2. And what that's saying is that if you squeeze the gas together, you decrease the volume, then the pressure increases. That's what happens when you put your hands on the side of a balloon and you push really hard on it. Sometimes the pressure increases to the point that the balloon pops. Okay, so Boyle's law also can be seen with the bicycle pump. So inside of this pump, there's a cylinder. You push it down. That pushes the gas particles closer together and increases the pressure. Pressurized air goes through the tube and fills up your bicycle tire with a higher pressure air than the surrounding atmosphere. All right, Charles' law. Charles was a balloonist and noticed that if you increase the temperature, that the volume also increases. That relationship is a direct proportionality. So this one ends up being modeled as V1 over T1 equals V2 over T2. So if you want to get more lift, you heat up the helium, and if you want to get less lift, you let it cool down or release some of the helium too. All right, and then Gay-Lussac's law related temperature and pressure. So basically, the higher the temperature goes, let me go back and just mention here. So this one related temperature and volume. So if it's not contained in a solid container, it'll get bigger. If it is contained in a solid container, like Gay-Lussac's law, then the pressure goes up instead of the volume. So the word for that is rigid. If the container is rigid, then the pressure increases. If the container is not rigid, like this, then the size or the volume increases. All right, so let's go back and look at this gas law simulation for a couple more minutes, and I'll try and show you some of those things as we're going. Okay, so let's see. I'm going to keep pressure constant and show you Charles' law. When you heat it up, it gets bigger, and when you cool it down, it gets smaller. Okay, if we hold the volume constant, then we can see Gay-Lussac's law, because as we heat it up, see the pressure over here is increasing, and then as we cool it down, the pressure is decreasing. And then let me hold the temperature constant, and we'll do Boyle's law. So I'm going to squeeze it together, and you can see that the pressure goes up as I make it more squeezed together, and as I release it, the pressure goes down. And if we're careless here, let's do this. If we're careless and we just keep heating, oh, by the way, if I put more gas in here, that's increasing in, that makes the pressure go up. But if we're careless and we just keep heating and keep heating and keep heating, This could be a real thing, say a boiler that's lost temperature control. Eventually it gets so hot that the pressure goes up so much that it blows the lid off. So there you go. Thanks for watching.